Hi, and welcome back. Let's continue the journey that we started with the previous lesson. Today we are going to complete the discussion on the aerodynamic forces by introducing the lift. What do an airplane, a kite, a sailing boat have in common? All the three machines use a component of the aerodynamic force called lift. An airplane flies thanks to the lift that contracts the gravity. Thanks to this force, the kites can make the spectacular acrobatics that you see now. It's the lift that allows the sailboats to sail against the wind. We can experiment with caution the existence of this force. Everyone who puts their hand out of the window while driving a car has experimented the effect of the aerodynamic forces. For different positions of the hand, we can obtain different actions. With the hand in horizontal position, we meet an old friend, the drag, which tends to push the hand backwards. With the hand slightly inclined, we have the lift. Our hand will rise towards us just like an airplane. If we incline the hand in the opposite direction, it will be pushed down, just like a Formula 1 stabilizer. Let's review all through an animation. Objects heavier than air, like this B747, for example, can exploit Archimedes' principle to win gravity, like balloons and airships. It's thanks to the lift that a B747 can sustain itself. Let's imagine that at takeoff with full payload, it weighs more or less 400,000 kilos. This force, produced by the interaction between the airplane wing and the air, is the key of the aeronautic technology. The lift allows flying the aircraft by opposing against gravity. Like the hand that you saw before, also the airplane has an angle with respect to the direction of its motion. The angle between the direction of the motion and the chord of the airplane's wing is called angle of attack. Now we see how the angle of attack and other factors have effect on the lift. On a flying airplane, other two forces act, the drag and the thrust of the engines. The thrust opposes to the drag, factors which affect the lift. How can we obtain all the requested amount of lift force necessary to fly the airplane? Let's start by observing which factors influence the lift intensity. The lift, which we indicate with the letter L, is directly proportional to the wing surface S and to the density of the fluid called ρ. Moreover, the lift is directly proportional to the square of the aircraft speed. If we double the speed, the lift will increase 4 times. The formula which gives the lift intensity is that shown. Lift is also proportional to a non-dimensional coefficient which depends on the angle of attack, called lift coefficient.
Funzione di alfa ed è denominato coefficiente di portanza.
We've already saw which factors influence the lift. Now let's ask ourselves, which are the basic physics principles of the lift? To answer this question, we need the third law of dynamics, called also the principle of action and reaction. Things work just like in the case of rockets that push a certain amount of gas towards down to receive a force in the opposite direction. In our case, the wing deflects the air particles downward, and the air reacts with a force which is the lift. Both in the case of the rocket and in the airplane, the reaction force is given by the variation of the momentum given to the fluid in the time unit. For the wing lift, will be equivalent to multiplication of the mass of the air moved down in the time unit, called m dot, by the variation of the average speed, delta v, produced by the wing in the air. In the animation that you see now, the airplane can be considered immersed in a flow tube that has a diameter equal to the wing span. M dot will approximately be air that flows through the tube. In the formula, the mass flow m dot is equal to the product of the air density ρ, the airplane speed v, and the cross-sectional area of the flow tube A. If the flow tube has a circular shape, its diameter coincides with wingspan b. If we want to obtain a particular value of the lift force, we can combine in various ways mass flow and average variation of vertical speed, delta v. For example, if the speed of the airplane decreases, the vertical speed given to the air must be increased. It can be obtained by increasing the angle attack of the wing. If we want to fly at a low speed without increasing too much the angle attack, we have to increase the wing span. It's now time to ask ourselves how much energy we need to have the lift. The wing transfers kinetic energy to the air through its movement. The variation of the kinetic energy in the time unit given to the air gives us the power we need to gain the lift force, as we can see from this formula. If we have two wings with the same surface but different wing spans, the power necessary to gain the lift force is less for the wing with larger span. Wings with a larger span can move a higher mass of air. Let's show it with an example. Suppose we want to obtain a lift force equal to 4 Newton. We can obtain it in two ways. For example, with a mass flow equal to 4 kilograms per second and a variation of vertical speed of 1 meter per second. With a mass flow equal to 1 kilogram per second and a variation of vertical speed of 4 meters per second. In the first case, the power needed will be only 2 watts, while in the second case we have to spend 8 watts to obtain the same lift. To keep the airplane flying, you need to give back in some way the energy that it wasted, as we saw previously.
La dissipazione di
The
energia,
waste of the
infatti,
energy opposes
determina una
to the aircraft
resistenza al
force
moto
called
dell'aereo.
induced drag,
Tale resistenza è la
DI, which is
resistenza
induced by the
indotta dalla
lift.
portanza. Dicono da induced drag in inglese. Per
It is
calcolarla,
given by equating the work done by this force in the time unit to the power needed to move the air downward, as outlined by the formula. This type of drag is added to the friction drag that every object is subjected to when immersed in a fluid. It gives indication of the pushing force we need to give to the airplane to obtain the lift. The ratio between lift and drag is called aerodynamic efficiency. The higher is the efficiency, the lesser will be the energy necessary to keep it flying. As a consequence, less fuel is needed. Let's see in detail what happens to an object in an airflow. The simplest case to consider is the airflow around a cylinder or a sphere. As you can see in the animation, the flow is completely symmetrical and the total force that acts on the sphere is zero. In this case, we are considering a so-called ideal fluid. In a real fluid, there will be the drag due to the friction and the wake. Let's now give a clockwise speed to the sphere in a real fluid. The rotating motion produces a circulatory motion in the fluid thanks to the effect of the viscous friction. This circulatory motion adds to the symmetrical one. Let's see what happens at point A. The speed of circulatory motion adds up to the basic symmetrical flow, and we obtain a net increment of the fluid speed. The opposite situation happens at point B. The speed of the circulatory motion is directed in the opposite direction, and it is subtracted to the basic symmetrical flow. According to Bernoulli's principle, and without the circulatory motion, pressure would have the same value at points A and B. With the circulatory motion, the pressure at point B is higher than at point A. This pressure difference produces an upward force on the sphere. Let's now see what happens for an airfoil. The same kind of circulatory motion that we had on the sphere or the cylinder happens even around a wing airfoil. This allows obtaining a lift force. Let's consider a wing cross-section that we call airfoil, which is a body with a sharp trailing edge. The motion of such a body in a real fluid produces tangential forces due to friction in the boundary layer and in the wake. These tangential forces make the fluid rotate. When an airfoil begins its motion, the fluid tends to turn around the sharp trailing edge. Since a very high velocity is needed to turn around the trailing edge, the flow separates and forms a counterclockwise vortex. This vortex is initially unstable, and after a few times, it is taken away. This vortex is called starting vortex, since it starts the production of the lift force. When the vortex goes away, it produces a clockwise circulation around the airfoil. This happens for the third principle of dynamics.
Allontanandosi dal bordo di uscita, il vortice di avviamento genera una circolazione uguale ed opposta intorno al profilo alare. Tale circolazione nasce per reazione a quella associata al vortice di avviamento durante la fase di accelerazione.
Let's remember that the conservation of angular momentum is valid. If the trailing edge is very sharp, both the production and the starting vortex and the circulation around the airfoil are quick phenomena.
Risultano molto rapidi.
Every change in the speed of the angle of attack generates a new starting vortex.
Dalla formazione di un nuovo vortice di avviamento.
In the previous chapter, we discussed about the lift by considering a cross-section of the wing called the airfoil. Indeed, the wing is a tridimensional object. How is the real flow around a finite wing? The circulatory motion around the airfoils creates two big vortices at the wing tips,
che si distacca dall'ala e che tende ad arrotolarsi a valle formando due nuclei vorticosi.
The intensity of these vortices is higher for low aspect ratio wing and for high lift coefficient. The vortex wake strongly interacts with the lift distribution along the wing because it influences the so-called downwash, which is the mass of the air that the wing pushes downward. For these reasons, also the induced drag is influenced by the vortex wake.
Concludiamo il nostro discorso sulla portanza, cercando di capire se esiste un limite alla forza di portanza che si può ottenere da una particolare ala.
We already know that the lift can be increased by increasing the angle of attack. The angle of attack cannot be increased too much because dangerous phenomena can occur.
Fino a che punto possiamo aumentare l'angolo di attacco?
The figure shows the lift as a function of the angle of attack. We can see that for little values of angle of attack, the function is linear. Above a certain value, the lift is not linear, and after a critical value, the lift does not increase anymore, it decreases. What happens on the airfoil? Behind the airfoil, a wide vortex region is present.
Che sconvolge la corrente principale, come abbiamo già visto nella scorsa lezione sulla resistenza.
It makes the fluid separate from the body. In this condition, the so-called stall
si separa
occurs.
dal corpo, dovendo fluire intorno alla regione vorticosa.
Just to summarize, when we increase the angle of attack until the critical value, the flow separates on the upper surface and the drag increases a lot, while the lift abruptly decreases.
Dunque, quando aumentiamo l'angolo d'attacco dell'ala per ottenere una maggiore portanza, se esso supera un dato valore critico, lo strato limite stalla sulla superficie superiore e la corrente principale si distacca da essa. La resistenza cresce notevolmente e, cosa ancora più importante, la portanza diminuisce di colpo.
The stall is a very dangerous phenomenon for the safety of the aircraft and the passengers. During takeoff and landing, the speed is low and the lift coefficient must be high. This means to increase the angle of attack near the critical value. In order to avoid the stall, the lift coefficient is augmented not only with the angle of attack, but above all with other surfaces called flaps. These devices increase the wing surface and the airfoil curvature, allowing to obtain the desired lift without excessive values of angle of attack.
Permettendo così un incremento sostanziale della forza di portanza. Anche per oggi abbiamo finito.
We've just finished. Now you can answer to the question, why does an airplane fly? Goodbye, and see you soon.
Alla prossima lezione.